Hello?
Hi, sorry, take a bit too long today.
Oh, it's okay, Joe.
Only another 10 minutes, sorry. Might as well, because anyway, I won't charge you. It's just other than hanging in the air halfway, then you can do some work. Okay, let's carry on. We are just trying some exercise. Okay, try this question. Just using this formula, Faraday's law. A coil of 1,000 tons at and of mean area 35 cm square is placed in air with each turn perpendicular to the uniform magnetic field of flux density 0.75 Tesla. Calculate the induced EMF if the field decreases to 0 in 5 seconds. Okay, try that. Right, now where to find your what formula to use? Where's your N? Where's your A? Where's your BI? Initial magnetic flux density.
So
Final
BAN.
is 0. Time is 5 seconds. We write the formula. Flux density is N times 5. So it's BAN. We write the equation. Put in your value. Okay, should be able to get 0.53 volt. Can get or not? Yep. Can or not? Can or not? Can or not? Remember to change your 35 cm square to meter by multiplying 10 to the power minus 4. Your A and your N are the constant. Your B is the one changing.
Yeah, I got that, teacher.
Good. Okay, let's do this example. A rectangular coil moving at constant speed V into a
This is the last one.
two more.
Okay.
Moving at constant speed V into a region of uniform magnetic field. The field is going in. That's a rectangular coil. That's the length that's inside. That's your width W. And that rectangle is a uniform region of uniform magnetic field going into the page. That's the area inside the field and it's moving with velocity V. right? So the area inside the field is omega W times L. That's your L, that's your W. Right? Flux linkage, BA, right? N is 1, so we don't put your N in. Then replace the A with WL, WL, and replace your L with VT. So if we look at that equation, this equation, your flux linkage, right? B is constant, W is constant, V is constant, it depends on time. Okay, so it's basically Y equals to mx plus C. Y equals to mx. Okay? Compare Y equals to this is your gradient, that's your X, that's your Y. So we draw the graph as it enters, and as it more and more enter, this completely enter, this coming out, this come out, this completely out, okay? This complete outside, this complete outside, this is where it's going in, it's completely inside there. Okay? Inside there, the flux is constant. So there's no change in flux, no change in flux, no induced EMF. So we apply that one there, right? We just use gradient. Okay, it's a constant gradient. And this part, gradient is 0, 0. That part, negative, negative, negative becomes positive. Okay. Anyway, I'll send you the video. You can since you want to finish fast, I'll finish fast for you. I'll send a video to you. You just listen. Okay. Two similar coil A and B of insulated wire are wound onto a soft iron core. When the current I in coil A, close the switch there, is switched on, then off, the variation of time t of the, you're given the graph there. So on the figure, this figure, draw a graph to show the variation with time t of the EMF induced in the coil. Right? Remember we say your B is proportional to I. And then we use your Faraday's law. So we differentiate. The thing that's changing is the current. Right? Differentiate the current. So it's di dt. So the E is proportional to gradient. Right? If you don't worry about the negative sign there. Then in this case, right, this part is the gradient is very sharp. Right? Very sharp, and then it decreases to 0. So that's how it could go. This part gradient is 0. This part is negative. Okay, as I say, I'm not worried about this negative sign, then that's how the graph should be. But yeah, you want to worry about this negative sign, then this is inverted. This one will be up. Okay, you go back and review. I just go over with you a bit faster. This is just to prepare you in the cell induction we will study later on. Okay. Okay, let's try one question. This one, what's the answer? Page 220, number 1. Diagram shows a uniform magnetic field. It's a uniform magnetic field. In a rectangular region, there's your copper ring moving through the position 1, 2, 3, 4. Which statement is not true of the changes experienced?
Answer is boy.
Okay, let's see. At position 1, there is no change in flux density, so no current. That one is wrong. Okay. They ask you not true. So A is correct. At position 2, there is an increase in magnetic flux and the current induced, correct. At position 3, there is a constant magnetic flux and constant current induced. If the flux is constant, no change in flux, no current induced, no EMF. So answer is C. Right? At position 4, there's induced current because part of it is changing as you move out. Position 4, there's a decrease in magnetic flux and a current is induced. So the wrong answer is just C. Okay? Inside there, no, it got motion, but the flux is constant. So no change in flux, no induced EMF. This one, number 4 in your book, page 220.
Okay, so number 1 was what, teacher?
Number 1, the answer is C.
Oh,
A metal rod has a metal rod, length L. That is your length, whole length, which is placed on 2 parallel conductors. These are your parallel conductors in a magnetic field. There's a magnetic field B, which is directly perpendicular into the paper as shown in the diagram. The 2 parallel conductors are separated by a distance. That's the distance, right? Small l, distance between the 2 parallel conductors, and connected to a resistor R. The metal rod slides at constant speed V. Which expression represents the applied force? Okay. Find the current, find the induced EMF first, and find the current. Then after that, use BIL. A bit more difficult. This one, a bit more complex. Right? Use that equation, E equals to B LV. Now, which is your L? Right? This is your L. That L, the length that is between the conductor, not the whole length, because the current doesn't flow through the whole length. And then from there, from the EMF, we can calculate our current, induced current, E over R. Right? That's your R. So it's BLV over R. Then you apply your BIL, topic 16, BIL. Right? Replace your I with your BLVR. So that's your answer. Can. One or two more there? Or two more left. Sorry about that. I thought better reinforce it. Okay, answer C. This one, number 13, page 222. Diagram shows 2 coils of copper wire arranged coaxial. Same axis there. Coil X, that's a coil X, is connected in series with a battery. A switch, that's your coil X, that's your battery, that's your switch, and that's your rheostat. Which of the following procedure will produce a current in the coil Y, which is in opposite direction to the current in coil X? So that's what you want. What's the answer? Yep. Can? That's what you require. Okay. You one is the North Pole, one is South Pole, or the two currents are in opposite direction, they repel each other. So look at the situation. Right? Where is the answer? Answer is where you look at this one. Unlike pole repel. Resistance of the rheostat is increased, you're changing the current only. So it doesn't affect the repulsive or if it's repelled, it will repel more as well. So it won't affect it. Y is moved away from X. If you move Y away from X, right? You want to oppose it, so you want to attract it. So that cannot be the answer. You want a repulsive force. Okay, X is moved towards Y, right? X is moved towards Y. So as I said, you are applying Lenz law. It's going to repel. So that's the correct one. No? Answer C. No? Unlike current, you produce unlike current. Rather than go to a complicated, using the polarity, which is a bit more complicated, understand that what is required, you want unlike current. You want a repulsive force. So only C will give you a repulsive force. Now you open the switch, you produce induced current in Y as well. Okay with that? Let's try this last one. Number 15. What's the answer? Coil is released from rest above a region of uniform field B. It falls vertically through a magnetic field. The diagram below shows the coil when it enters the magnetic field B inside the field B. There's a field B. There's a coil. There's outside. It's inside. It's coming out. Which of the following correctly states the direction of the current induced in the coil when it is in the position as shown above? Yep. Using your Fleming's right-hand rule. That's the Fleming's right-hand rule. Okay, the field is going in. It's moving down. Inside there's no this one, no current. So when it's entering, it's anti-clockwise. You look at this part there, you should go to the right. So answer is C. So if this is anti-clockwise, then when this is same, these two is the same direction. These two, right? This one anti-clockwise to the right. This one will also to the right, but this one will be clockwise. Can or not? Your thumb, this one, your thumb is moving down. Thumb is going downwards there. Your B is into the page. Your thumb is going downwards there. The field is going into the page. So the current is going to the right. Okay. Thumb is going down. That's a motion. Field is going in. So the current is going to the right. Okay. You're looking at this part there. Okay. I'll send you the video. So if you are okay, we'll stop here today.
Okay, Chair.
Okay. Have a good day.
Yeah, you too, Chair. Thank you. So Saturday.
Saturday we'll sell induction. No, Saturday we'll solve problem for you. Answer all your questions.
So far we studied 2 subtopic already lah.
2 subtopic. You should be able to do checkpoint 17.1, 17.2.
Yep.
And then we'll spend time answering your questions Saturday. No?
Okay, easy.
Bye-bye.
Bye-bye. Chair, if I ask other question, other chapter can?
Ken, you want to ask question? We will give you time to ask question on Saturday.